Welcome back to Honors Calculus. In this video, we're going to be looking at the extreme value theorem. The extreme value theorem is one of what are called the big three theorems in calculus: the intermediate value theorem, the extreme value theorem, and the mean value theorem. They're called this because they are very technical in their proofs. They rely on the completeness axiom, which we've talked about previously, and they are also linked in that they are existence proofs, not derivation proofs. So these proofs all tell us that a thing exists and give us no tools on how to find that thing. We'll develop the tools for this particular one a little bit later on in the course. For right now, just knowing that it works is going to be pretty good for us. Let me get my head out of the way and let's talk a little bit about what we're going to be looking at that is going to be so extreme. So we're going to build a set with the values of a function taken over some interval. When we've looked at functions in the past, we've generally focused on the x values, but here we're going to be looking at our function. We're going to be looking at our endpoints, a and b as usual, and we're going to be tracking y values so that we grab all of the values that the function can get to on that interval, not the interval itself. But now that we have this set, we can talk about the things that we've talked about previously. We can talk about the upper bounds and the lower bounds. We can talk about the greatest upper bound and the least upper bound. And those things all certainly exist and they're all interesting. But the one that we're going to really care about is the maximum and the minimum. Remember, the maximum is an upper bound that appears in the set, and the maximum is always the least upper bound when it exists. The minimum is a lower bound which actually appears in the set, and the minimum is always the least upper bound, or I'm sorry, the greatest lower bound when it exists. We have no guarantee that the maximum and the minimum will actually exist, but when they do, they are worth talking about. The extreme values, the maximum and minimum of the function, right? So extrema or extreme value is the collective term for the maximum and the minimum. Also, to make things a little bit messy, depending on the application, it's not always clear if we want the x value or the y value when we're talking about that maximum or minimum. Generally speaking, what we're really going to be looking at is the value of x, which causes the maximum, the value of x, which causes the minimum. If you have those, it's generally very easy to go back and actually calculate what the maximum or minimum is. If what you have is the maximum or the minimum itself, it's not always easy to go back and figure out when that happens, right? Evaluating a function versus solving for the roots of a function you've seen in the past is quite a bit different in its needs. Once again, before we can get to the extreme value theorem itself, we need another tool along the way. We call this the boundedness theorem. And oddly enough, the only requirement we need is that a function be continuous on a closed interval. And if that is the case, then the function will be bounded on that closed interval. There will be an upper bound and a lower bound. I suppose that makes sense because the only times that upper bounds and lower bounds don't really exist on functions is at the end behavior or at vertical asymptotes, places where the function is not continuous. But it's still nice to bring all of that together and actually try to prove that result. Right? I'm only going to prove half of this. For a function to be bounded, for a set to be bounded, it has to have an upper bound and a lower bound. We're going to find the upper bound, or we're going to show that the upper bound exists. We're not going to look for the lower bound. But once you see the proof, it's pretty easy to go back and rewrite the same proof, just looking at things with inequality symbols flipped over. So this half of the set will be good enough. We're going to look at the set I'm going to call set X, which is the set of all x in the interval from a to b, such that f is bounded above on the interval from a to x. Right? And as I write this out, I want to note that the degenerate case, a itself, on the interval which begins and ends at a, It's the closed interval, so it includes the point A. Well, that's the only point, right? The interval from A to A is the point A. So the values of f of x on this interval are just f of A. Since f is continuous, we know that f of A exists and it has a finite value. So f of A will satisfy the need for a least upper bound. It is an upper bound on this set. It's also a lower bound, but we said we don't care about lower bounds for this part of the proof. But you could use the exact same logic going through and doing this again for lower bounds. Then we use the same logic we've used before. This set is a weird set, but it's a subset of an interval. And an interval, a closed interval like this, a bounded interval, is bounded below and also bounded above. So any subset must be bounded below and bounded above. And every interval is a subset of the real numbers, and every subset of a subset is a subset of the original set. Right? That means that the least upper bound of this set is going to exist. I need a name for it. I'm going to go into the Greek alphabet and choose the letter beta because it kind of looks like B. And we care about that because we want to show that beta is in fact B. These are the same value. And then we are good to go. We know that because B is an upper bound on S, that the least upper bound beta has to be less than or equal to B. Let's assume that beta is strictly less than B. And since A itself is definitely in this set, beta has to be greater than, I guess, greater than or equal to, given the singleton nature, but we're going to assume that there's more than just one point in set S. So that means that the least upper bound has to be bigger than the lowest point, A, which means that this beta is somewhere in the open interval from A to B. And we know that f is continuous on this interval. So the limit as x approaches beta of f of x is equal to f of beta. All right, we don't have a lot of tools, so we have to use all of them, right? We know that the function is continuous. That was the one assumption that we had. And so because the function is continuous, we will define, or we'll write down the limit, and then we'll use the limit definition. We can pick any value of epsilon that is convenient to us. It turns out that epsilon equals 1 is going to be convenient. Why do I know that? Black magic. I went off to the side before I started writing this proof down. I did the entire proof. I figured out that epsilon equals 1 gives us a really cool result. And so I know that that's going to be something, right? Because the only thing that matters is that epsilon is somewhere bigger than 0. 1 is bigger than 0, so that works. All right, so absolute value of f of x minus f of b is less than 1 whenever x minus b in absolute value is somewhere between 0 and delta. And we can expand out these absolute value inequalities. All right, -1 is less than f of x minus f of beta is less than 1. Opposite of delta is less than x minus beta is less than delta. F of beta minus 1 is less than f of x is less than f of beta plus 1. Beta minus delta is less than x is less than beta plus delta. All right. And here we're going to get a mess showing up on our hands. That first inequality gave us that f of x is bounded. We have a lower bound and an upper bound. The second inequality gave us the interval on which it is bounded, which is from beta minus delta to beta plus delta. But we already said that beta was the least upper bound of the set of intervals. So the interval from A to beta is the least set where f is bounded. But if we simply union it with this, interval from A to beta plus delta. All right, well, we don't quite get closure there, so we have to choose something between beta and beta plus delta. I'm just going to call it delta star. It's anything smaller than delta. 0 less than delta, star less than delta. So that's somewhere inside this interval so that we can get the closed bracket on the endpoint here. I can use symbols. Beta plus delta here is bigger than beta. We said that beta was the upper bound. We found that we had to have something bigger, right? We said that beta was the upper bound and that the interval from A to beta was the largest interval starting at A where f was bounded. And then we saw that f was bounded if we extend out just a little bit further, which means that beta isn't actually the upper bound, there is something bigger. Once again, this is a proof by contradiction. We must have made a faulty assumption. And the one assumption that we made was that beta was strictly less than the endpoint B. And so it must be the case that that assumption was wrong, leaving the only other possibility left, beta is equal to B. And so we get the conclusion we wanted. This function is bounded everywhere. As I've said before, the ideas of proof by contradiction can be a little bit hard to follow sometimes. Setting it up and figuring out why we did the things we did is not straightforward in a proof by contradiction. So as you're looking at this proof, the goal is that you can understand and you agree that each step is valid. Whether or not each step makes sense in the sense of, I could have figured that out, is beyond the scope of this course. I'm looking for each step makes sense in the sense of, yes, I agree that that follows the rules of mathematics. All right, but that gives us the boundedness theorem. And now that we have the boundedness theorem, the extreme value theorem is actually pretty easy to get to from here. Let me get my head out of the way and let's continue onward. All right. Once again, our only assumption here is that we have a continuous function, a function continuous on a closed interval from a to b. With just that, I claim that there are two values. I called them c and d just to pick some things sequentially, somewhere inside that interval, so that f of c is the maximum value and f of d is the minimum value of f of x among all the values of x in that interval. Just like we did with the boundedness theorem, I'm going to show you that the maximum happens. I'm not going to worry so much about the minimum. Right? By the boundedness theorem, we know that this function is bounded. By the completeness theorem, we know that if we have a bounded set, the least upper bound exists. Our goal is to simply show that that least upper bound is, in fact, the value of the function. And once again, we're going to proceed using some contradiction. let's assume that f of x is always strictly less than the least upper bound and never equal. And so we'll define a new function, g of x is 1 over f of x minus the least upper bound. I'm just going to call it LUB, just because I'm tired of writing out all of that. All right, so LUB, the least upper bound of f of x on the interval from a to b. We know what it all means. We can use simpler notation. Mathematicians are inherently lazy, and if we can get away with writing fewer letters, we're always going to. And since our function is in fact still continuous, or since our function never hits the least upper bound, g of x is also a continuous function. I'm sorry, I wrote this backwards. I need the least upper bound minus f of x. That will in fact make a difference, but the logic is still the same, but the sign SIGN there is going to make a difference. Right? But we still have boundedness, right? G of x is continuous on AB, so that means that G of x is bounded. We can pick some upper bound, I'll call it K. It doesn't have to be the least upper bound, it's any upper bound in this case. And then I can play around. All right, what do I know? Least upper bound of the function has to be bigger than the value of the function. So least upper bound minus the function is positive. That's why I had to go back and fix that earlier. Because it's positive, I can multiply both sides of the inequality. Right? That, like I said, that makes a difference. That denominator has to be positive because the least upper bound of the function is bigger than or equal to the function, and we've assumed never equal. And so we can multiply, we don't have to worry about changing the inequality at all. And then just doing some algebra. Rearranging that equation, solving for f of x, we get that f of x is less than or equal to the least upper bound minus 1 over k. We found a smaller upper bound than the least upper bound, which means that our least upper bound is not the least upper bound, which means that we made an assumption that must have been wrong. And the only assumption we made was that the function, or that the least upper bound didn't occur in the function. And so that's how we know that the maximum value must actually occur. As I said at the beginning of the video, we'll be looking later on at how to find when and where the maximum value and the minimum value occur. Turns out that there's some pretty nice theorems for that, but for right now, knowing that they exist is good enough. I don't have an actual problem for you on this one. The theory here, the vocabulary here is all that we really have to work with. So in order for me to see that you have in fact watched this video all the way to the end, I would like you to write in the what I was saying, sorry about that. I would like you to write in simply that max f of x is equal to least upper bound f of x. Just that statement is good enough so that I know that you watched this video all the way to the end, and I'll see you next time.